Okay. Good morning. So, this point of time, we just wanted to come to the last topic, which is left out in the module 3, right? So, the focus on today it's going to be on the application of the 8085 microprocessor. Basically, it is. So, we are just going to look at two of the basic applications. One application is on with respect to the traffic light control, and the other application is with respect to the stepper motor control. Okay, so these are the two applications that we're just going to focus on. And on this part, we will be looking at one of the component that we have already seen as one of the peripheral devices, the device namely 8255. Okay, so that's one peripheral that we will be using on these two applications to make sure that our objective of the control of these two parameters are being taken into consideration, right? So just before proceeding, let me know is the slide is visible. So right now the slide which I'm showing you is on traffic light control. Just on your chat box, just drop a message whether the slide is visible and I'm audible, right? Yeah. Okay. Fine. So let's first get into the first application of traffic light control, right? Here, any application for the matter, we just will have a problem statement which says about what is that we are going to do, right? So for this particular traffic light control, the problem statement that we have considered is design of a microprocessor system which will follow a particular sequence. The sequence is what it is given below, right? As we already know that traffic light control, we normally look at a road with 4 directions, right? North, south, east, and west. Okay. So the sequence that is available here is something like this. First point, we need to allow the traffic from west to east and east to west transition for 20 seconds, right? And then we are going to give a transition period of 5 seconds. Why is this transition period? Is to switch over between green to red. And during that point of time, our out of the 3 lights, red, yellow, and green, our initially when the direction is from west to east and east to west, green will be glowing in that direction. Okay, and when during this transition period, an yellow light will be glowing, and then the sequence will be north to south and south to north. It is the third step, allow traffic from north to south and south to north for 20 seconds. Then on that particular direction, we are just going to put it a transition of yellow bulb on for 5 seconds, and this process continues. Okay, but normally the traffic that we follow is not like that. We start with the north direction, then we go to east, then south, then west, and that's how the cycle gets repeated, right? It depends on the user part. You can design on anything, right? For an application like this, right, for a problem statement like this, when we just look at, this is a schematic of a traffic light show where we have got all the 4 directions which is available to us: north, south, east, and west. And our statement which went was initially to let the signal from east to west and west to east, right? It's not going something like this, no crossing of west to north and west to south. It is only a straight line, straight traffic from west to east and east to west, then north to south and south to north. Okay, don't think logically, think on this problem statement. Okay, and we have just considered initially with only 3 lights, red, yellow, and green, represented as R, Y, and G. But the pedestrian crossing, turn left, turn right, uh, go straight, those indications are not considered on this particular process, right? That's why I'm saying you don't think logically, but for the basic concept you can think like this, right? So keeping this in our mind, 4 directions, each directions having 3 LEDs or 3 color lights, one for red, one for yellow, and one for green. So altogether we have got 12 number of lights available, right? And each of the direction is represented with a numerical, right? North is represented as R1, Y1, G1, and west is represented, south is represented as R2, Y2, G2, west with R3, Y3, and G3, and east with R4, Y4, and G4, right? Now, When we say that there are three ports available in our peripheral, namely port A, B, and C, right? And out of those three ports, one of the port is with, again, subdivided into an upper port and a lower port. Okay, so in that three ports available, we are here going to consider port A and port B. Port C, it varies with application, right? For this particular application, I need 6 number of my port pins to be ready on each of the port. Port A, I am having 6 number of lights connected. Port B, I am connecting 6 number of lights, right? So for north and south, R1, Y1, G1, R2, Y2, G2. I am using my port A. Out of the 8 pins available in my port A, PA0 to PA7, I am using PA0 to PA5. 6 pins I am using, right? Similarly, from west and east, for R3Y3G3 and R4Y4G4, I am using my port B. PB not to PB7 was available, but my requirement was limited to only 6. So I have chosen my PB0 to PB5 for R3Y3G3, R4Y4G4. So any interfacing for the matter, your initial step after getting clarity with your problem statement, focus on the port assignment. Okay, so interfacing will always be successful only when your port is assigned properly, right? So once when this port is assigned, the next step is to find out how your interfacing diagram will look like, right? Out of the 3, 4 peripherals which we have studied, A255, A259, A279, we are going to have use of A255 here, okay? And as I said, that out of the 3 ports, we are using port A and port B, and out in that 8 pins plus 8 pins, 16 pins, we are going to limit to only 12 pins. So my PA0 to PA5 is there, PB0 to PB5 is here, right? And each of this port, it is connected to a light through a freewheeling diode, right? So it is not only with PA0 and PB5, it is with all the other pins are also, it is connected in the same mannerism, right? And this is a latch signal which is available here to go on for a chip select of this case, right? And this side which you find here, AD0 to AD7, A0, A1, IOR, IOW, these are the areas which will get a signal from your 8085 microprocessor, okay? And you will find this part of your 825 is connected to your microprocessor, okay? And just as I said, there are port A, port B, and port C. Initial case is like we have to map our ports, different ports available so that it gets interfaced properly with my 8085, right? So what I'm doing is I am just connecting my port A with this address line of A0 to A7. I will initialize it like A80, 81, and 82. So these are my initializing address which I am assigning for my port A, port B, and port C. And for a control register, 83 is my address which I am mapping with, right? So having done that, now is the step is where we have to initialize this 8255. Okay, to initialize this 8255, what we do is we give a control word signal to that 8085 and 8255 so that it gets initialized, right? So this is how your control word is being generated. One for BSR IO mode, and for mode A it is 00, port A is 0, port C higher, port C lower is a don't care case, just because we are not using that port C in our structure. Port B is again assigned to 0 and mode B is assigned to 0. So leaving behind 1, 000, don't care, 00, don't care. So that means it is 8 here and 0 here. So my control word for initialization of 8255 stands to be 80H. Okay. And this is how my the next step, which light to glow, and for that particular glow of light, what should be my output for my port A and port B. Okay, for a thing like R1, R2, G3, G4 to glow, right? Understand here the first step, R1, R2, G3, G4. R1, R2, G3, and G4. That means direction is from west to south, west to east, and east to west is available, while north to south and south to north is with red color indication. Okay. So at that point of time, here you will find for R1, R2, G3 and G4, you will have to come back to this port 1, R1, R2. What is the pin numbers connected? PA0 and PA3. And again for G3 and G4, it is PB1 and PB5, right? Now, PB, G3 and G4, PB2 and PB5 are connected, right? And similarly for R1 and R2, it is PA0 and PA3 is connected, right? So now if you look at the word statement here, split this into 4 bit and 4 bit. So for the first 4 bits, it is don't care, 1, 0. That means it is 2. For this case, it is 0, 1, 00, it is 4. So for this port B, it is 24H is my value that I should have at my port B, right? And for this port A, it is 4 bit of first one, it is 0. And for this case, it is 1001, it is 9. So it is 09. Okay. So if my processor is giving an output to port A as 09 and to port B as 24, then this is the light that will be glowing here. Okay, how this glows is because of the initialization of this 8255 done using a control word of 80H, and that is because of initializing of these ports, right? So this is for one particular sequence of direction of flow from west to east and east to west, right? Now coming to this case, all these 4 yellow lights have to now glow for 10 seconds, right? So for yellow light, what is that we have given? PA1, PA4, PB1, PB4, right? So it is PA1, PA4, PB1 and PB4, leaving behind all the other things as 0 and these two pairs as don't care case. Okay. Now when you combine when you look out for this 4 bits, it is 1, here it is 2. So that is 12 is here for port B, and similarly it is 1 and 2. 12 is for port A. Right? And the next step is from north to south and south to north will be green, and east to west and west to south will be with red. Okay. Excuse me. Okay. So here, if I just look at this point of time, it is R3 and R4 are with are supposed to be 1, G1 and G2 are supposed to be 1. Okay, so R3 and R4, PB0 and PB3 are supposed to be 1, and G1 and G2 are supposed to be 1. Okay, so that is nothing but PA2 and PA5. Okay, so that is how it is being done here, and its corresponding port A and port B values are marked. Okay. So after doing this is our program area, right? So we have now got the different values for all the 3 sequence, and this sequence continues. Look at the problem statement: west to south, east and east to west for 20 seconds, then 5 seconds for yellow glowing, then north to south and south to north for 20 seconds, 5 seconds for yellow glowing, then it continues, right? So this 3 thing along with 12 and 12 here, after this particular 3rd row, 4th row will be again 12H and 12H, then the 4 rows will get repeated again and again, right? So this stands to be our program, where the initialization of my 8255 is done with my control word 80H. So 80H is what I have got here, right? So that I'm assigning, moving immediate to my accumulator, then I'm that outing that to my 83H. 83H is my control register. Okay. So once that is done, then we start to go with a sequence of 1 by 1, right? So what is that sequence? You look at here. It is 09 is first one, 24, 12, 12, 24, 9, 12, 12. So that is going to be my sequence. So what I'm going to do is, first one, the 9 is what the value is there. That I'm immediately moving it here. That value I am outing through port A0. Why 80? Why 80 is this 09 is what I want in my port A. So port A have given my address as 80. Okay, so it's outing to 80 just because it is through port A, and this is what my number is. 09 is the data. Then I'm coming for immediately transferring this 24 to A. 24 is nothing but the value that I should have for this sequence in port B. And port B, it is 81. So that 24 is moved here and 81 is done here, right? And then it is 28. What is that 28? So that 28 is nothing but the delay sequence that I'm going to introduce. What is the delay sequence that we have been looking out for us? A 20-second of, for a period of 20 seconds, these two lights have to glow, right? So that is being introduced intentionally here as a multiplier count for a delay. The 28, its equivalent decimal is 40. So that will be looked into the delay program. And it goes to a delay program, which we will see later. After this delay program is executed for 20 seconds, it comes back to this main program where this 12 is my data that I should have for all the 4 yellow lines to be glowing, right? So I'm moving immediately this 12 data to A, which I'm outing through my port A and port B, right? Sorry, by mistake it is port A, it should be 80. Yeah, it is 80H it's supposed to be, okay, and 81 is for my port B. So both these ports will now hold a data of 12. That means all these 4 yellow lights are going to glow. And then I have requested for a delay of 5 seconds, right? In your problem statement, you said yellow light should go, the transition time for should be for 5 seconds. Madam? Just a minute. Yeah, hope now the screen is visible. Right? Yeah, so that yellow lights will be glowing for 5 seconds. So that is an multiplier count which is inserted here, like what we had inserted here for 20 seconds, right? So here this is for 5 seconds, so we are introducing here. And again the delay program will run. After the delay is over, it comes back to the main program. Again in the main program, I'm going to give the earlier value of this 24 and 09. Okay. So that 24 is now available here, which I am outing through port A, and then 09 outing through port B. Okay. Then there is a time delay of 20 seconds, which is introduced here through this 28H for this north-south lights to glow. Okay. And east-west red color lights to glow. Okay. Then we have got this 5 seconds of all the yellow lights to glow. So that is introduced here. Right? And finally, just to make sure that the process gets repeated continuously, I've introduced a statement called JMP start, right? So it jumps to the start. Start is nothing but it is available here, right? So it jumps back to the first condition of my east and west green color light glowing and my north and south red color light glowing. Okay, and the sequence will get repeated continuously. Okay, and this is my delay program, right? So in the delay program, we are just making sure that the delay data that we have given there initially of whatsoever might be the multiplier count that we are giving there, right? So the multiplier count which I meant was this. Your C register is having a value of 28 in this case, and your C register is having a value of 0A is in this case. So it depends on whether it is for 20 seconds or is it for 5 seconds. Right? So this C register is what I'm going to use here. The decrementing of that C register is done here, right? So if that multiplier value is 0, okay, then it goes back to the main program. If that value is not 0, then this delay program will continuously be running ahead, right? So this is with respect to our traffic light control using our 8085 microprocessor. right? Uh, just take a moment of time to copy down few of the things, right? The few of the things are going to be, first one is understand the sequence, you can write down this problem statement first of all, okay? And then the second point is draw this diagram. Third one is assign the port. Fourth one is my interfacing diagram. Fifth one is this, sixth is this, and then the program, right? So hope I have made clear of this, how the traffic light is controlled using 8085. Is that clear? Is that clear? Yeah, thank you, Sedu. Somebody from AMB. Is the application of 8085 for traffic light control is clear? If it is not clear, let me know where it is not clear so that I can think of clarifying that. Or otherwise, if it is clear, you can start to copy down the things on the screen, right? Let me switch on to the next slide. Okay. Okay. Thank you, Uma and Pratyusha. Somebody from C section. Shall we move on to the next application? Okay. Fine. So it's very simple. If you are in campus, then you might have had a hands-on work on this particular traffic light control also on your lab component of working on this traffic light control module, as well as with the interface of 8255 and 8085, right? So it purely matters of how you are going to make this port values, right? So based on this port values, based on this sequence that you want to follow, your port value changes. And based on these port values, you are going to out through which port, whether it is through port A or port B or port C. Port C, of course, we are not going to use it. So that's why we are given it as don't care case here, right? So port C lower as well as port C higher or port C upper or with don't care cases. Even in port A and port B also the last 6 and 7 pins, right? So that also we have this 4 pins are also it's not being used here, right? It is purely left to our option. If you are going to increase the number of lights, right? So if in case you are going to add a pedestrian light for each of the directions. So pedestrian crossing, that means you should have a red color light and then green color light for pedestrian crossing, right? So you need two lights for two direction. So 4 directions, 2 into 4, 8 lights are needed. So then you can use this 2 which is available here. These 2 are available here. You can borrow the other 4 required pins from your port C also. So that provision is also available. At that case, your control word will get changed based on whether you're going to use port C higher or port C lower. And here in this, instead of this don't care, it might vary. And port C also comes into picture here. And port A, port B, and port C comes in between, right? So it's purely left to your application and your assigning of your control word and your data that you want to out through which port, whether it is port A or port B or port C, right? So that is all to do with your traffic light control. Now let's move on to the next part, which is the last topic that we are going to discuss is on about the control of a stepper motor, right? So a motor we are aware of, but what is the stepper motor is all about? Something like when you are using a printer, a dot matrix printer for a matter, you will always find that your paper when it rolls out after printing will come in terms of a step rotation of your the drum, right? So that's by the use of a stepper motor. The variation of the voltage which is given as an input will come as an output through a step angle variation, right? So whether it is a half step or a full step, it depends on the application, right? So a stepwise variation of each voltage that is applied to it uh, to a motor is a particular a stepper motor is what we are going to have here. So here we are going to interface a stepper motor here to our 8085 microprocessor system, and we are going to run that in any of the direction, either in clockwise direction or in the anti-clockwise direction. Okay. So what is that stepper motor basically is? It is a permanent magnet called rotor is available, which is surrounded by a stator, right? This rotor also we call it as a shaft, like arrangement, right? And the most common stepper motors will have 4-stator winding. With that 4-stator winding, there will be a center tap which is available, right? What is the purpose of the center tap is to make sure the current direction in each of the coils which is available on the windings will be made. Okay, based on the current direction that we want to give, it is being done through the use of a center tap which is placed in between the 4-stator windings. Okay, and this setup of arrangement is what we basically call it as a 4-phase or a unipolar stepper motor, right? Just because there are 4-stator windings, it is 4-phase stepper motor, right? And when you start to interface your stepper motor, you cannot do it directly, even through 8255, right? The reason behind is very simple. Even a small stepper motor will require a current somewhere around 400 milliamps, right? So in that case, if you are going to connect this with the 8255 or 8085, then that might cause some damage to your port. Okay, so what we do is we rely on a driver circuit which can withhold a current requirement of 400 milliamps. So to that particular driver circuit, I'm going to rely upon a driver circuit called ULN2003. Okay, so this is an IC which is readily available to us, which is a high voltage, high current Darlington transistor array, and this can give a current of 500 milliamps. But my requirement is only 400 milliamps, right? So this IC holds to be a particular aider for me to have this particular application driven, right? And as I said, this current is sufficient to drive a small stepper motor, right? And so that is why we are going to use this ULN2003 as a driver circuit or an interface to your stepper motor to the microcontroller or a microprocessor, right? At some point of time, you might find the word microcontroller available, no issues. Your 8051 or 8085 or 8086, anything for the matter, you are going to use an interfacing circuit, and that is having a driver circuit, in this case as ULN2003. Okay. The operation, as I said, there will be a step-wise variation. The most important parameter here is a step angle, right? What is a step angle? It is a minimum angle through which the motor rotates in response to each excitation pulse. Whenever a pulse is given, what is the minimum angle that my motor can rotate? Okay, so what is here available is, in a 4-phase motor that we said no initially, there are 200 steps for one complete rotation. Okay, then the step angle will be total complete direction is 360 degrees, right? So 360 divided by 200, which is close to 1.80. Okay, so 1.80 is a step angle which is for my 4-phase motor which is available with us. Right, so I'll be converting this into a hexadecimal code, and that again, as how we did for traffic light control, we are going to feed it through a port which is assigned here. Right, here you will look at your microprocessor is available here, which is connected to your 8255, and in between your 8255 and your unipolar stepper motor or your 4-phase stepper motor, you have your driver circuit, ULN2003 driver circuit, right? So this is what is your hardware connection is all about. And yeah, this is what is our device connection. Okay, and even in my traffic light also, we had a decoder circuit, 74LS138 for a chip select decoder circuit for our 8255. This decoder will be always available when you are going to use an 8255. Okay, and here unlike your traffic light control where you have your predetermined sequence, here it is again a predetermined sequence, but the predetermined sequence is only based on the step angle. Step angle, as already I said, it is 360 divided by 200. 1.8 is my step angle. So that 1.8 is the hex code that is applicable here, and that is what is that will run through each and every phase. Okay, so the first phase is here. 77 is my first control word address. There we had 80 as a control word address, right? Hope you remember this control word of 80 for initialization of 8255. Here instead of 80, I am going to rely upon my control word register 77. right? So that I'm outing through port TA. That will be a delay program. The delay program is for that 1.8 pulse step angle one. Then we will give for each and every phase variation. This is for phase 2, it is BB. For phase 3, it is DD. And for phase 1, it is EE. Okay. So this is once every time when I'm moving this data value to my port TA, that will be assigned out through port TA. And then it is on DD to port TA for again for third phase, EE to port TA for first phase, and the process will completely continue. Okay. So this port TA address here, it is left blank, right? But the port TA for traffic light control, we have given an address, right? So that is where we find a difference. 80H was an address which was data which was available, right? Similarly, you can make your own frame of the data also available here. Instead of this port A address, you can, based on your bits assignment of that port A and port B, here we are going to use only port A, no port B and no port C business is available here. So for that, you can assign a port address and give that address at all times, right? And this is typically your delay program that is introduced here for a step angle variation. Okay, so for running in clockwise and anti-clockwise direction, only one variation is required in your stepper motor, right? Instead of this J and Z, if you can put that as JZ, jump on no zero, if it has been transferred to jump on zero, that runs in the opposite direction. Program wise, it is very simple, right? So that is to do with your interfacing of your 8085 with a stepper motor, right? Only additional feature is a driver circuit is introduced in excess here, right? For a particular reason, like it needs a 400 milliamps. That is not possible with my 8255, as it might cause a damage to ports available there. So I rely upon a driver circuit which can hold 500 milliamps. Okay. So that ends my traffic light, the stepper motor. So just make a note of this hardware connection. We always look at this whether the driver circuit is introduced here or not, right? So your hardware connection is required, device connection, then your program, right? So just you can copy down this hardware connection. Okay. So with that, we'll conclude that we have completed the all the topics which are associated with module 1, 2, and 3. Okay. And this was the two topics this was a single topic with two subdivisions which was left out in the module 3. Okay. So that we have concluded now. Okay. So having said this, the next part from now onwards will be revision, right? Revision from starts with module number 1, and then we'll move to module number 2. Okay. In the meantime, you might all have received the information, like we are going to have a CA3 with multiple choice question, and in that multiple choice questions, again we are going to have higher order thinking skills of questions which are going to be available, right? So there you will have to, we are going to give you a program like things, and you will be asked to determine what will be the output of the program, or we will give you a data and ask you to rotate this as left or right, and then we will ask you what will be the nature of the output after that. Rotate accumulator right, or rotate accumulator left, rotate with through carry, rotate right through carry, and so right. So those part also we will see somewhere in the Saturday's class, right? And as we have already said that today afternoon we'll have our model lab 1 for digital electronics, right? So that we will work on today. Okay. So in the meantime, for the next 35 minutes, we are going to work on, we're going to have a revision of the part called module 1 on Quinn QM method, right? For under minimization of a Boolean expression, we had got two methods, right? One is K-map and the second one was QM method. Oh, hope you can remember this. This was happened in a long way back, somewhere in the 2-3 months before, right? But then, hope you remember. Just note down the question which is available on the screen, right? So that's going to be your question. We are going to have a 5 variables of A, B, C, D, and E. And your minimization min terms are nothing but 2, 5, 8, 9, 12, 14, 18, 24, 27, and 30. Right? So this is an expression which is available to you, and this you are expected to minimize using by QM method. Right? So as we are aware that there are two methods, K-map method and QM method. K-map, we normally do it for when the number of variables is limited to 2, 3, or 4. And when it gets more, then minimization with the K-map is quite tough, so that we rely upon this QM method. Okay. So in this QM method, I'll just let you know what we were discussing. Okay. So in this QM method, what the first step that we will do is, we will group these terms, min terms which are available here, keeping in mind of the number of ones which are available there in the min terms. Okay. Say for example, my first min term is min term number 2. That has only one number of 1 which is available there. My 2 can be represented as 00010. So that means one number of 1 is available. But when you look at the value of 5, min term 5, then that is 00101. So there are 2 ones are available. So then you will have to arrange this min terms based on the number of ones and group them also. Group them in the sense, whichever the min terms which are with one number of ones, group them as one group. Then 2 number of ones, second group. 3 number of ones, third group, and it continues. Right? So that's my first step. Second step is, I'm going to compare each of my min term of each group with a subsequent group. My first element of first group will be compared with the first element of second group, second element of second group, third element of second group, until the last element of the second group. Right? Then I will compare my second element of first group with the first element, second element, third element of the second group. Then my comparison will be between the second group and the third group. Then it will be between third group and fourth group. It continues, right? Based on the comparison, then I will move on to my next column representation, where whichever is comparable will be now brought into the second column, right? Whichever is comparable, we are going to mark with a tick mark, and whichever is just non-comparable, which we are going to mark it as leave it as just like that, or we are going to put a cross mark, right? So for whichever we have marked the tick mark, we are going to combine them into the second group. Then even in the second table, we are going to have the comparison between each and every group, subsequent groups. There I'm going to put a tick mark, whichever is comparable, right? That will be moved on to the third table and it goes on, right? And finally, we are going to find out which is the prime implicant and which is the essential prime implicant. Okay, so that's a plan of going for the QA method. Hope you have copied down this question. So I'm just now going to stop presenting and the screen will be now focused onto the board. Okay. Is the board clear? Is it visible? Yes, no? So, just as I said, we are just going to find out the first column that we are going to form. Okay. So this is my column 1, where I am going to have all these midterms which are available here will be arranged in big letters. Okay. Increase the font size. Okay. So what I will do is first I will represent all my midterms here. Okay. So the midterms are first let me write down what are those terms. So this 2 is what I'm going to represent it as 00010 and then 5, 8, 9. So 5 will be 00101 and 8 will be 01000, 9 will be 01001. And then it is 12, 18, 19, 24, 27, and 30. Okay. So 12 is going to be like 01100. 18 is going to be like 10010. 19 is 10011. And 24 is 11100. 27 is 11011 and 30 is 11110. Okay, so here I'm going to first find out the number of midterms which are with one number of ones, which are nothing but this midterm number 2 and midterm number 8. So these are the two midterms are with one number of ones which are available here. So I will first write it here in my column as 2, 8. For 2, what was the value? It was 00010, and for 8 it was 01000. So this is my first group. Okay, and my second group is I'm going to have two number of numbers, which are 5, 9, 12, 18, and 24. Right? So 5 is one in the first one. So 5 is represented as 00101, and that will be followed by 9. 01001. Then it is 12, 18. Okay, so for 12 it is 01100. For 18 it is 10010. And for 24 it is 11200. So this is my second. Okay. And my third group is whichever the midterms which are the free number of ones. So the free number of one is only the one with 19. Okay. So 19 comes here like with 10011, and then with 4 number of ones are my 27 and 30. 27 and 30. Okay. So 11011, 0. Right? So hope this is clear. I have marked all my midterms available here with its corresponding binary values. And in that I am counting my number of ones in each of the midterms. And based on the number of ones which are available, one number of ones I am marking that as first group, two number of ones as second group, three number of ones as third group, and four number of ones as fourth group. Okay, just copy down the question as you have copied, then come here and then move on to this part. Right? Just copy it down. If you are done, let us go. Then we move to the next step. Okay. I'll just erase this particular part. We have space for things there. Okay, as now I have my step 1 as column 1. Now I'm going to use my next step, step number 2 as column 2. Okay. So what is that we are going to do is, we are going to compare each of the midterms available in a group with a subsequent group. For example, let me compare my 2 and 5. My first element of my first group with the first element of the second group. By the term comparing, what I am trying to say is, I am going to compare each and every bit which is available here. 0, 0. Okay, there is no change. 0 and 1, no change. 0 and 1, yes, there is one change. 1 and 0, there is again another change. 0 and 1, there is third change. But what is parameter is only one number of bitwise variations per bit. Okay, but when I compare my 2 and 5, then there are three number of bit variations. 0 is now here as 1, 1 is available as 0, 0 is available as 1. So when I compare these 2 and 5, this comparison doesn't fetch me a result. Okay, so 2 and 5 I'm going to drop. Then I'm going to compare my 2 and 9. Okay, 0 1 0, there is no big change. 0 1 1, first change. 0 1 0, no change. 1 and 0, second big change. 0 1 1, third bitwise change. Again, this 2 and 9 doesn't mention the result. Right? Now then, when we compare my 2 and 12. Okay, 0 and 0, no change. 0 and 1, change number 1. 1 0 and 1, change number 2. 1 and 0, change number 3. 0 and 0, no change. So there are 3 number of changes. Again, this doesn't hold good. Now I'll compare my 2 and 18. Okay, 0 and 0, 0 and 1, first big change. 1 and 0, sorry, 0 and 0, no big change. 0 and 0, no big change. 1 and 1, no bitwise change. 0 and 0, no big change. Fortunately, I am having only one bitwise variation when I compare my M2 and M18. Right? So what I will do is I am going to consider this as my first element in my column 2. Okay, 2 comma 18 is what is going to be available here. 2 comma 18. Okay, under that 2 comma 18, what is that value which is available here? Which bit is having a variation? 0 and 1. Maybe the first bit is having a variation. So that I will put the reference as dash. Okay, maybe the other 4 bits I will write as 0, 0, 1, 0. Hope this is clear, right? So when you compare two midterms, you are expected to be permitted with only one number of bit variations. That is possible when I compare 2 and 18. So that's what I have written there. The dash corresponds to the bit where the variation has happened. 0 is now available as 1. Okay. So what I will do is, once when this 2 is getting satisfied, I will put a tick mark to this and this. Do that first of all. Okay. Then I will start to compare my 2 and 24. My 2 and 24, when I start to compare, 0 and 1, first variation, 0 and 1, second variation, 0, 0, no variation, 1 and 0, third variation, 0 and 0, no variations. 3 bitwise variations, yes, 2 and 24 doesn't work out for me, right? So then I will write down 8 and 5. The second element of my first group. With the subsequent group, all the elements. Okay. So 0 and 0, no variation. 1 and 0, first variation. 0 and 1, second variation. 0, 0, no. 0 and 1, third variations. 3 bitwise variations. So 8 and 5 doesn't work out. Then 8 and 9, 0, 0, no variation. 1 and 0, no variation. 0, 0, no variation. 0, 0, no variation. 0 and 1, only one variation. So 8, 9 is possible. 8, 9 is possible. Okay, that I'm going to represent the bit variations available at this particular point. Okay, so while the remaining other terms are no bit variation. So 0, 1, 0, 0, 0, 1, 0, dash. Is that clear? Now, how do we get this term? Right? Now let me compare this 2 and 12. Okay, 0, 0, no variation, 1 and 1, no variation, 0 and 1, first variation, 0 and 0, no variation, 0 and 0, no variation. So 8 and 12 also works out for me favor of 8, 12. Okay, and the variation of bit is happening in my third bit, right? So that resulting value will be 0, 1, dash 0, 0. Is that clear? So the variation is at this third bit, 0, 1. So the third bit is there marked with the dash 1 and this complete. Then 8 and 18 is my second comparison. 0 and 1, first big variation. 1 and 0, second big variation. No variation between 0 and 0. 0 and 1, third variation. 0 and 0, no variation. So there are 3 bit variations, not acceptable. 8 and 24 again. 0 and 1, first bit variation. 1 and 1, no variation, 0 and 0, 0 and 0, 0 and 0, no variation. So the variation is only with the first bit. So 8, 24 is also acceptable. 8, 24. Okay, and the resultant of that value is dash 1, 0. Dash 1, 0. So this completes our comparison of my group A and group B. Okay, so I will put a dash here. Right. Now what I will do is I will start to compare each of these elements which are available at group B with group C. So this is my group C and this is my group B. Okay, so now the comparison will be between GB and GC. Right? Look at 5 compare with 9. 0, 1, first variation. 0, 0, no variation. 1 and 1, second variation. It's dropping. 9 and 19. 0 and 1, first variation. 1 and 0, second variation. Overlook. 12, 19. 0, 1, first variation. 1 and 0, second variation. 18 and 19. 1 and 1, no variation. 0 and 0, no variation. 0 and 0, no variation. 1 and 1, no variation. Last bit, 0 and 1, only one variation. So this is acceptable. 18, 19 is acceptable. 18, 19 is acceptable with a value of 1, 000 dash. 18, last bit is 0, here it is 1, so that is marked as this. Okay, this has to be changed. Thank you. It will be 1001 dash. Is that right? Yeah. Now let us compare the last element of group B with the element of group C. 24, 19. 1 and 1, no variation. 0, 1 and 0, first variation. 0 and 0, no variation. 0, 1, second variation. Third variation. So that is also not possible. So GB and GC would be discussed. Right? So 8 was already compared. So I'm going to put a tick mark in 8 also. Right? And 9 was already compared with 8. So 9 is also going to have a tick mark. 12 is already compared with 8. 12 is with a tick mark. 18 is compared with 8. No, 18 is compared with 12. So let me give a tick mark. Right? And 24 is also compared with 8, so that is also going to have a tick mark. Left out is only this 5, I'm going to put a cross mark. Here, 19 is now compared with 18, right? So 19 will also have a tick mark. Okay. So now we are going to come with comparison of group C and group D. Okay. When I compare here, 19, 27. 1 and 1, no variation. 0 and 1, first variation. 0 and 0, no variation. 1 and 1, no variation. 1 and 1, no variation. So 19, 27 is possible with the resultant value as 1 dash 0 double 1. Is that right? Since it has been already compared, then we are going to take up here. Now coming to the comparison of 19 and 30. 1 and 1, no variation. 0 and 1, second variation, first variation. 0 and 1, second variation, no variation. 3 variations exist. So again, this is not comparable, leaving behind the minus dash. Okay, so this completes our second step. Okay, as how we did comparing each of the element with the subsequent element, try doing the same thing with this. Compare each of this first element with the subsequent element, second element with the subsequent group first element, and these two elements. Just compare and find out if anything is with one bit variation. If it is with more than one bit variation, just leave it. Okay? Just take a moment and try to find out if that forms a tick mark or a cross mark for each of these terms. Right? Find out. can the comparison be made possible here? 2 comma 18 with 18 comma 19 dash and 1. Yeah, there is one variation 0 and 0, no variation 0 and 0, no variation 1 and 1, no variation 0 and dash. Second variation. So this comparison is not permitted. 0 and 1. First bit variation 1 and 0. Second bit variation. Then the 4 bit variations when it is between 8 comma 9 comma 18 comma 19. That's also not acceptable. 8, 12, 18 and 19. 0 and 1. First variation. 1 and 0. Second variation. Drop. 8, 24, 18 and 19. First bit variation. Second bit variation. Drop. So for all these cases we get a cross mark. Okay, compare it as 18, 19, 19 and 27. 0, 1 and 1, no variation. 0 and 1, first bit variation. 0 and 0, no variation. 1 and 1, no variation. Dash and 1, again, there is a variation. So this is also a possible. Okay, so if there has to be any tick mark which is available in any of the element, then that takes shifted to a power 3. Okay, so now just because every column is every elements are the cross mark, we are going to limit this here and we will move on to the next step where we are going to draw the permittable table, primitive, right? So just highlight these 6 elements here, which are nothing but 2 comma 18, then 8 comma 9, then 8 comma 12, 8 comma 14, 18 comma 19, and 19 comma 27. Right? Along with this, I am just going to write which are the midterms which are available here. Okay, the midterms are nothing but 2 is one of my midterm, then 8 and 9 are my next midterm. 8, 9, then 12, 14, 18, 19 and 27. 12, 14, 18, 19 and 27. Okay, so back about my midterms which are available there, I will put the cross mark 2 comma 18. So 2 is 1 cross, 18 is here. Okay, then 8 comma 9, 8, 9, then 8 comma 12, 8, 12, 8 comma 14, 8, 14, then 18 comma 19, 18, 19, and 19 comma 27. Okay, after drawing this table, why do we draw this table? Is we are just going to find out if any of these terms, pair of terms, can be considered as non-essential prime element. When I say non-essential prime element, when I consider these and this, can I work out without this? So something like that I'm going to find out, right? So looking at here, you will find a pair of values like this. So this cannot be dropped because there is no other cross marks which are available. So this has to be there. So this should be there. When I look at these two cases, this is okay with other 2 cross marks are available with the subsequent midterms, but this is available only once. So this again cannot be dropped. So this is an essential prime duplicate. And here again, yes, it's an essential prime duplicate because here it's okay with, but this is available only once. So if I'm going to remove this complete row, my 12 is available only once. So that cannot be done. So again here, 8 comma 14, 14 is available only once. So of course, it's mandatory. Then look at 18 comma 19, right? 18 comma 19. This is here. This is here. Right? So in case if I am going to consider this 18 comma 19 as a non-essential prime duplicate, no big changes is going to happen because of the row 2, 18 is going to map with 18, and this 19 is going to be compensated with 19, 27. Look at this pattern. So this is standing to be a non-essential prime implement. This my 18, 19. While 19, is this mandatory. Right? Just the purpose of drawing this primitive table is to find out which is non-essential prime implicant and which is essential prime implicant. So out of the observation from this, I find this 18, 19 as the term which is a non-essential prime implicant, while the other terms are essential prime implicant. Okay, so that is how we conclude, and finally we will have to write the equation leaving behind this 18, 19 alone. Right? So what will be the subsequent values of this one? So when you look at it here, right? So this is nothing but A, B, C, D, E. Bitwise relation. Okay. So look at this term, 2, 18. A is a down case. B, C, yeah, or with that is nothing but B bar, C bar, D, E bar. So this is for my 4, 18. For 8, 18 it is A is equal to 0. So that means A bar, B, C bar, D bar is a don't care case. When it is in 8, 12 it is A bar, B, C is not going to come into picture, whereas D bar, E bar comes into picture. D bar, E bar. Okay. Coming to the 8, 24, it is A is going to be ruled out because it is don't care. B, C bar, D bar, E bar. And for 19, 27, it is A, B will not come here. It will be C bar, D, E. Finally, write an equation like y is equal to, put all the 6 terms, 1, 2, 3, 4, 5 terms with a plus sign in between, and that now gives you a problem. Finally, mark a statement like prime implicants are shown above on the equations, and non-essential prime implicant is 18, 19. What is that 18, 19 is? A, B bar, C bar, D is my non-essential prime implicant. Okay, so that completes your problem. Okay, so it's high time. Let's start with this for this particular class. After we will come for the digital electronics part. Okay, for modern. So as Madam told yesterday, focus on the first 6 experiments. Out of that, you will get 1 experiment. You will have to write the